Hi there, welcome to Pink Ink. In today's video, let's try to understand the importance of 2's complement, how it is useful for binary arithmetic, especially in the case of subtraction. In order to understand this, let's try to use a 3-bit binary numbering system. In 3-bit numbering system, we will have 3 bits and let's try to represent them as B2, B1 and B0. And the weights of these 3 bits would be 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. So with these 3 bits, we get a total of 8 numbers ranging from 0 to 7. Let's try to illustrate this 8 numbers using a number scale like this: 0, 1, 2, 3, 4, 5, 6 and 7. So in this numbering system, let's consider 2 numbers for our exercise today, right? So let the numbers be A and B. A is represented here, and similarly B is represented here. So with these 2 numbers on this number scale, let's try to find out what is A minus B. So as you can see on this number scale, this quantity here represents A minus B, and this is what we need to compute in today's class. So how do we do that? Let's get to that in a while. Before we do that, let's do some more computations and then see how we can arrive at A minus B. So let's consider the number 8 also in the numbering scale, even though 8 is not possible to represent using 3 bits of binary numbers. Hence, I am marking them a little differently. The number 8 is marked differently on the number scale because it cannot be represented using 3 bits of binary numbers. Let's try to find out what is 8 minus B. As you can see from this numbering scale, the quantity 8 minus B is this particular line. Let's try to add A with 8 minus B. Right? So in order to do that, let me bring the A or redraw the A here. Right? So let's add A with 8 minus B. So what we're trying to do is A plus 8 minus B. When you do that, you can see here the quantity A is going to come in as this, and this portion of 8 minus B would also come in. And all of this together now amounts to 8. So this is going to be 8. So far what you have, this portion is 8. So the remaining portion of 8 minus B, which is this portion, is going to come in here. So this particular region or this particular segment of 8 minus B is nothing but A minus B. So that's what ends up coming up here. So A plus 8 minus B results in 8 plus A minus B. Right? Now lies the importance of 8. So this 8, since it's not representable using the 3 bits of binary that we have, so this 8 in the result is non-representable. So which means this is something that we can ignore or it's kind of irrelevant. So the 3-bit number that you would end up with is just going to be A minus B. That's what we'll have in the result. So as you can see, by a simple addition operation here, we are able to arrive at A minus B, right? So we are able to add A with 8 minus B to arrive at a minus b. Now, what is this 8 minus b? It does involve a subtraction also, right? So are we not really are we really not using subtraction here? That doesn't seem like the case, right? So we seem to be having a subtraction here. So what is this 8 minus b? So 8 minus b is nothing but 2's complement of b. This is what 8 minus b really means. 2's complement of a number is the subtraction of that number from the max possible number with the n bits that we have. If you have n bit binary system, so 2 power n minus the number, let's say b, would give you the 2's complement of the number. So in this case n is 3 because we have 3 digits of binary. So it's 2 power 3 minus b, which is 8 minus b. Right? So this is what 2's complement gives us. So by adding the 2's complement of b to a, we can get directly a minus b. That's the advantage of 2's complement. Let's find out a little bit more. Let's work this out with an example. Let's try to find out how to compute the 2's complement here. The steps involved for computing 2's complement are twofold. One is invert all the binary bits of the number. Second is to add 1 to the number, to the inverted number. So let's take an example with a equals 5 and b equals 2, and our aim is, or objective is to find a minus b, which is 5 minus 2 equals 3. So in order to do this, let's first start by finding the 2's complement of b. So 2's complement of b, b is nothing but 2. In binary it is represented as 0, 1, 0. Step 1 involves invert all the bits, which would be 1, 0, 1. Step 2 would involve adding 1 to it, say plus 0, 0, 1, let's say. 1 plus 1 is 1, 0, so 0 here and a carry here. 1 added with all the zeros here would be 1 here, and 1 plus 0 is 1. So this gives us 6. 6 is nothing but, if you closely look, it is 8 minus 2. 2 is b, right? So b. So 8 minus b is what we got here as 2's complement. And as you can see, without having to do the 8 minus b operation, just by inverting the bits and further adding 1 to it, we are able to arrive at the 2's complement without having to do any subtraction. That is the advantage of 2's complement method. So we arrived at 6. Now let's add a plus the 2's complement of b. Or in other words, 8 minus b, right? So a here is 5. In binary it is 1, 0, 1. And I would just say 2's complement of b is 6, which is 1, 1, 0. Let's add these two, see what we get here. 1 plus 0 is 1, 0 plus 1 is 1 here. 1 plus 1 is 2, and in binary it is 1, 0. So 0 here and a carry, so which can be come as a fourth digit here. So as you can see, the 3 bits here represent a value 0, 1, 1, which is 3. And this 1 represents actually the 8, right? Because it's on the next higher digit, which we do not have, so we cannot use it. So it's basically representing 1 followed by 3 zeros, which is 8, which we don't have. So this 1 here is referred to as a carry, something which we can drop or ignore or not considered again going forward, right? So as you can see, by adding a with 2's complement of b, we're able to arrive at the difference of a and b with a carry which we can ignore. So this is the advantage of using the 2's complement method, where with simple bit manipulations followed by an addition operation, we can arrive at the difference of two numbers. Let's take the case when A is less than B. Right, so let's just reverse the values of A and B, like A equals to 2 and B equals 5. So in this case, let's see what happens to A minus B. A minus B would be 2 minus 5, which is equals to minus 3. So let's try to do this same operations here and see how it results. First, let's try to draw this out on the line diagram. A little bit of, let's try that. So let's represent 0, 1, 2, 3, 4. D. So A is 2, which is this quantity. B is 5, which is this quantity. And this is going to be 8 minus B here. As you can see, no matter what we do, the addition of A with 8 minus B in this case will not result in numbers that is greater, that's going over 8 and then giving us the A minus B. It doesn't seem like it. So let's try to follow the same method here, like adding A with the 2's complement of B and see what does it yield us. So let's take the 2's complement of B in this case, right? Let's start with that 2's complement of B. So B in this case, as you can say, is 5. So binary wise it is 1 0 1 5. Let's invert them first, all the bits. That would be 0 1 0. Let's add 1 to it. So it becomes 1 plus 0 is 1, then 0 1 1. You can see it is 3. So this is the 2's complement of B, which is nothing but 8 minus B or 8 minus 5, right? And that's what you have B as. B is 5 here. Let's add A with 2's complement of B. A is 2, so in binary it is 0 1 0, and the 2's complement of B we computed as 0 1 1. So it's 2 here and a 3, and you will see the result as 0 plus 1 is 1, 1 plus 1 is 2, and 2 in binary is 1 0, so 0 goes here and there's a carry. 1 when you add it with all zeros, you'll get 1 here. So basically it results in a number 5, and then there is carry position is 0, basically no carry. And in this case, though, we do see a carry, right? So when A is greater than or equal to B, you would see this sort of an operation by adding A with 2's complement of B resulting in a carry. So the carry indicates that the number that is there in the 3 bits is a 2 representation of the A minus B. Whereas in this case, it's not a 2 representation, right? Here you can see there is no carry, and the value that we get is 5, whereas we are supposed to get a minus 3 here. Now, how does 3 and 5 compare with each other? So if you take the magnitude of this minus 3, which is 3, and find the 2's complement of 3, right, which is 8 minus 3, we get a value 5, and that's what we have here. So when the carry that is generated is equal to 1, then A plus 8 minus B gives us a true positive number and gives us the value of A minus B, and it is a positive number. If carry equal to 0, then A plus 8 minus B gives us 2's complement of A minus B, and it's a negative number. So by looking at the value of the carry, we can interpret the results in 2 different ways. If the carry is equal to 1, then we're getting a positive number. If carry equal to 0, then it's a negative number, and that's how we can conclude what result is there with us. So as you can see, this is the easy way of doing subtraction of 2 numbers in binary using the 2's complement method. Thank you.